Good evening, everyone. Today we will continue with the topic on IR spectroscopy. In the last class, we have seen about the various IR spectra of hydrocarbons. So today we will have a look at other functional groups. Okay, so the first functional group will be an alcohol. The alcohol presence of the OH group is easily recognized by the presence of this broad peak in this region. So this is due to the OH, and the reason it is broad is because of hydrogen bonding between the different alcohol molecule. So in a liquid form we will see a spectra like this, but if you take the spectra in gaseous form, we'll see only a sharp spike, and due to the OH stretching. Okay, so that is the characteristic of alcohol group. Now not only that, we can also sometimes recognize this OH, but this again is in the fingerprint region, so it's a bit difficult to identify. So sometimes it's possible to identify, like this sharp peak here, which is due to the carbon oxygen stretching. But the more diagnostic peak is this peak in this region, and we also see again the same kind of peaks, that is due to the CH stretching there. So this is about the alcohol spectra. Now next we will have the ether. In ether, the hydrogen of alcohol, we can say, is substituted by an alkyl group. So in this example, the characteristic here is that we have the sharp CO peak. So this is very prominent event in presence of even though it's a fingerprint region, this sharp peak, which is almost 100% absorbance, is very prominent for ether. So within the region of 1050 to 1150 wave numbers. And another thing is that we saw that there is no more OH peak in this area of the alcohol. So this can be used as a way to identify between an alcohol and an ether. Suppose if they are isomers. Now let's move on to the next. That is the primary amines. Now in the primary amines, the spectra is like this. We have this peak here, which is a doublet. In the previous session I have discussed how NH2 will show this kind of a peak. So this is one of the important peak to identify an amine. So again, it is in the same region as that of an OH, and it's just after the CH groups. So here we have the amines peaks. Now additionally, this will have what is known as a deformation band around 1590 to 1650 wave number. So if suppose there is nothing that will disturb this region, then you can identify that one for an NH. It is still an NH stretching, but it is a deformation band. Okay, sometimes, but this is not very diagnostic, in the region of 780 to 820 wave number. So around this region, these are called as wag band due to the wagging of the NH2 group. So if we look at the difference between a primary amine and say a secondary amine. Now in a secondary amine, the main differences is this band here, where instead of a doublet, now we have a singlet, and also from a weak, now it is a medium band. And this particular region is about 32 to 3500 wave number. So between 3200 to 3500 wave number, we have a sharp peak. Now one thing to note is that tertiary amines will not have this peak. So you can easily identify between a primary, secondary and a tertiary. So tertiary amines will not be having this peak here. Okay, so that's about the amines in general. Then let's have a look at the aldehydes. How do the spectra of aldehydes look like? In this example, that is cyclohexyl carboxyldehyde, we have this peak. Now one of the very prominent peak is the carbonyl group. So the carbon oxygen group has a sharp peak in this region. Okay, so that is around 1720 wave number to 1740 wave number. But this band, they are sensitive to conjugation. Just like all carbonyl groups, they are sensitive to conjugation. So if there's a conjugation, it might shift the bands slightly, a little bit to lower frequency or to higher frequency depending upon the type of conjugation. So we will see about that later, which is a very important part because you can identify between different carbonyl groups having similar structures. And then one of the important thing here is that we have also an sp2ch stretch in this particular point. So this is a doublet. One is at 2720 and around 2820 wave number. So here we can not see clearly, but this is a doublet. There are two peaks over there. Okay, so that is due to this CH. So that means you can understand that this CH here can show that particular peak. So you can easily identify that. Now if we look between an aldehyde and a ketone, first thing you'll notice is that the absence of that doublet in that region, because a CC stretching is somewhere in this region. Okay, but we can clearly see this prominent carbon oxygen stretching within this region, that is a region of 1700 to 1725 wave number. Again, this is subjected to presence of conjugation and other groups also. Then let's move on to the carboxylic acid. Now this also is a carbonyl group, but one of the characteristic or the most prominent feature we can see here is that the OH band is overlapping all the CH stretching frequency there. Okay, so that is a characteristic of a carboxylic acid. It's just slightly lower than that of an OH, is somewhere around here. So for an alcohol, it will be somewhere around here. It will not overlap usually with the CH stretching in this region, but a carboxylic acid will usually overlap, and it's also quite broader compared to that of an OH group or an alcohol group. Then apart from that, we will also see the CO stretching frequency at around 1700 to 1725 wave numbers. Then the ester. So again, just like alcohol ether, the OH stretching is gone. Here also there is no more OH stretching in that region. So we have the usual carbonyl group in the same region, and also we can sometimes identify this peak, which is sharp and also very prominent peak, that is the carbon oxygen peak over there. But again, this is the fingerprint region, so sometimes it's not possible to identify, and sometimes it is possible to identify. Moving on to the next acid derivative, we have the acid anhydrides. The acid anhydrides also, they have this carbonyl group stretching. Now because there are two of these, so they tend to couple with one another due to the presence of this oxygen atom here also. So because of that, we have a kind of a doublet. So it's in the same region, but we have a doublet, not a singlet like in the other. Okay, so because of the coupling between the two carbonyl group. So this you can easily identify an acid anhydride by this couple around the same region of a carbonyl carbon-oxygen stretching frequency. Okay, then we also have this sharp, strong peak of a carbon-oxygen peak. So these two characteristics of an acid anhydride. Then we'll move on to the next one, that is the acid chloride. The acid chloride has this characteristic structure. It's cleft. It's a bit clefted over there. It's not a sharp, but it has got this cleft looking like structure. But again, it's due to the carbon-oxygen double bond. So the region is almost in the same location. Now you can see here it's around 1800. So between 1700 1800 like that, that is the region of the carbonyl group. And one of the interesting thing here is that we have this carbon chlorine stretching frequency, slightly lower, but it's quite prominent and you can easily identify that. In fact, because chlorine is slightly a larger atom, so if you remember the Hooke's law that I explained, then this will lead to absorption at lower frequency. And because of that, among the carbonyl halogen or carbon halogen bonds, the only carbon halogen that will show in the spectra is of that of chlorine. Usually the others, because they are slightly larger, they will not be able to show, they will not appear in the spectra. Okay, so that's one thing to remember. Then the amides. The amides, they also have these particular stretching frequency of the carbonyl. So you have the carbonyl group, and apart from that, we also have the amide group, that is the NH2 group there. So if it is in this case is an NH2, so it's a primary amine, therefore we'll have a doublet similar to that in the case of an amine. If suppose this is a secondary amine, then we'll have only a sharp singlet there, and if it is a tertiary amine, then this region will not be there. Okay, so this carbonyl stretching frequency is in the region of around 1640 to 1680 wave numbers. So this is about the amides. Then the nitriles. These are probably one of the most prominent that you can identify, because there's the CH stretching frequency that is here, and very clean looking spectra. The CN group absorb at higher frequency compared to the CO group, and is somewhere in this region. So this sharp, strong peak. So that you can identify for all the nitrile groups. So these are the different groups of other functional groups apart from the hydrocarbon that we have seen in the last lecture. So we have seen the alcohol, we have seen the ether. Alcohol has a broad spectrum, ether has missing that OH group spectra, and then we have the carboxylic acid. We also have the derivative of the carboxylic acids, and then we also have the amines, the primary amines, the secondary amines, which has peaks in these regions, and also we have the tertiary amines, which doesn't have that peak in that region. Okay, so this is how you identify the different functional group using IR. So in the next class, we will see some of the deviation if a functional group is present along with, say, a conjugation, or is present with other groups, how it affects the frequency or of absorption. See, sometimes it might lower the frequency, or sometimes it might increase the frequency, and from that you can say identify between two different compounds. Or if suppose you are given two spectra and you were given two probable compound, then you will be able to say this is the spectra because of this compound, and this is the spectra because of the other compounds. Okay, so that's all for today. Thank you.